we will see what is a computable function, then how to denote this computable function, then how to construct a Turing machine for computable functions. Then we will demonstrate some example problems. So when you can say a function is computable, if it can be computed by a Turing machine, then that function is called as computable function. A Turing machine is very simple machine, but logically speaking, Turing machine has all the power of any digital computer. So this is the importance of Turing machine. That's why Turing machine is most powerful computational model among all the models. So Turing machine may be described as a Turing machine processes an infinite tape. In simple terms, a Turing machine may be described as a Turing machine processes an infinite tape. So then a Turing machine may be viewed as a computer of functions from integers to integers. So with a function by using only integer values. So there are several conventions or notations commonly used in Turing machines, but we adopt the convention that the number are represented in unary notation. So any integer I greater than or equal to 0 is represented by the string 0 power I. For example, here, if we have I equal to 1, so this can be represented in the unary form with 0 power I. So that is equal to 0 power 1 equal to 0. Suppose if I equal to 2, then this can be represented in the unary form 0 power I equal to 0 power 2. If you can expand 2 zeros. So if you have more than one string, suppose if you have X and Y, two strings are there, both are separated by a digit 1. So this can be represented first 0 power X, then 0 power Y, then both are separated by a digit 1. So like that you can represent. This can be stored on the Turing tape initially. So then finally, while construction of Turing machine, the final configuration, what it contains, the result of this function will be stored on the Turing tape, then the Turing machine halts. So that is the concept of construction of a Turing machine for computable functions. Now let us see, if a function has k arguments, let us say I1, I2, I3 and so on ik. So a function with k arguments or parameters denoted by I1 to ik can be represented as, so in the unary form, so all the arguments are separated with digit 1. So that is first argument I1 is represented as 0 power I1. Then second argument is 0 power I2, then separated by digit 1. Similarly 0 power I2, then 1, then third argument 0 power I3, then separated with 1 and so on 1. Last argument is 0 power ik. So in the concept of computable functions, so how these are all represented means using unary string, then separated by digit 1. So furthermore, if you want to compute function f of n1, n2 and so on nk with k parameters, we assume that initially the tape consists of n1, n2 and so on nk properly enclosed, with each separated from the previous one by a single digit 1. Here what we mentioned here, see. So every string or argument is separated with a single digit 1, and with the tape head initially positioned over the leftmost bit of the first argument. That means suppose 0 power I1. I1 is the first argument. So in this first argument, the leftmost bit wherever it is stored on the tape, so the read-write head will be positioned at that bit of the first argument. And the state of the Turing machine is some initial state. As usual in the design of Turing machine for a language also, same concept. Then let m equal to f of n1, n2 and so on nk. If f of I1, I2 and so on ik is defined for all I1 to ik, then the function f is called as total recursive function. So in any computable function, so if that function is defined for all the arguments, then that is called as total recursive function. So a recursive function f of I1, I2 and so on is computed by a Turing machine is partial recursive function. So if any recursive function computed by a Turing machine, that is called as partial recursive function. Then partial recursive function corresponds to recursively enumerable language. What is recursively enumerable language? Which is type 0 language, which is accepted by a Turing machine, which gives the result as only yes. That is, it is semi-decidable, not full decidable. Since they are computed by a Turing machine, that may or may not halt on given input. Whereas recursive language means on each and every input, the Turing machine halts. So then that is a total recursive function. If any function that is defined for all arguments, then that is called as total recursive function. Then total recursive function corresponds to recursive language. Recursive language means which gives both results yes and no. This is full decidable language. Since they are computed by Turing machine that halt on all possible inputs. So now again here the concept of recursive and recursively enumerable languages are linked with this computable functions. So that is a recursive function which is computed by Turing machine is called as partial recursive function. Then that partial recursive function is corresponds to recursively enumerable language. Then the total recursive function is corresponds to recursive language. That is the relationship between recursive enumerable language to then total recursive function and partial recursive function. So then let us see the examples. So you will get questions like this. Construct a Turing machine M for successor function. So the function is defined as with mapping from n to n, f of x equal to x plus 1. So we have to construct a Turing machine for this function. So what you have to do here, so any given function, initially what you have to do, you can find out what are the arguments in that function. You can represent all the arguments in the form of unary, that is 0 power I. If more than one argument is there, each arguments are separated with digit 1. So initially that can be placed on the tape. So now let us see first here. Let us take given function f of x equal to x plus 1. X is a parameter or argument. So we have only one argument, parameter or argument, and is denoted by the string. So how to represent this one? 0 power x. So whatever the x value, so unary representation, unary number 0 with power the argument. So if you have more than one argument, then you can add digit, then you can concatenate with the other argument. So now initial configuration of the tape. So what we have to consider here? Initial configuration. So here let us assume, let us say x equal to 3. Then f of x equal to x plus 1, that is f of 3 equal to 3 plus 1 equal to 4 is the output. So this will be finally on the Turing tape. So therefore in initial configuration you can represent 0 power x equal to 0 power 3 equal to 3 zeros. So can be stored on tape. So this is the initial configuration. So therefore the tape consisting of here 3 zeros followed by blanks. Then what is the output here? What is the output or final configuration? So final configuration or output is 0 power 4. That will be on the tape, then the Turing machine halts. So here output is for x equal to 3, let us say f of x equal to x plus 1 equal to 3 plus 1 equal to 4. This can be represented in the form of 0 power 4, again a unary string, that is equal to 4 zeros. So this is the output that can be placed on the tape in the final step of the Turing mission. Here 1, 2, 3, 4, then followed by blanks. So now our target is we have to derive this one. So in the input configuration, you can see we have already 3 zeros, but here 4 zeros are there. So one extra zero is required. How to get this extra zero? See, after reading all symbols from left to right, you can skip all zeros until you will get first blank symbol. Whenever first blank symbol is occurred, then what you have to do, whatever the thing required, that you can replace with blank symbol. So we need one extra zero. Therefore, the first blank is replaced with 0. Then it moves right. Then it halts. Then it satisfies the output, that is x plus 1 successor function, like any value of x. So this mission satisfies if you will do like this. So now let us take steps. First, take the configuration, 3 zeros followed by blank symbol. Now the finite control will be at Q0 state, then read or write head will be positioned at the leftmost bit of the argument. Here only one argument is there. So step 1, what you have to do? First, step 1, keep all zeros until a first blank is found. A first blank is found. Then the transition for this is therefore delta of from Q0 on input 0 without changing state. 0 is replaced with 0, then skipped, it moves right. Now this is the first transition. Then see the configuration of the tape now. So here diagrammatically also you can represent. Now, so this first 0 is skipped. Then the control will be in the second cell with same state without changing state. Then you can skip this one also. The second 0 also you have to skip. Then your control will be at the third 0 cell. Then again this 0 also you have to skip using the same transition. 0, 0, 0, then blank. Now the control will be at the cell where blank is available. So now then come to second step. So whenever first blank is found, replace blank by 0 and moves right and then halt at accepting state. Now you can see for this, now the transition is delta of Q0 on blank, first blank is found. Now you are replacing blank by 0, then it goes to new state. Q1 blank by 0, then it moves right. Now this is the transition corresponding to this one. Here Q1 belongs to F. Why? Because finally this is the halting state. Now the configuration will be like this. So now 0, 0, 0. Now blank is replaced with 0. Then it moves right with Q1 state. Then after 0, what it will contains? Again blank only. So here Turing mission halts at Q1 state, which is accepting state, which is called as accepting state. So now you can see the final configuration. Therefore, here 1, 2, 3, 4, 4 zeros are there. Therefore, the Turing machine halts by keeping x plus 1 symbols on tape. Now you can see if you can take x equal to 3, 3 plus 1, 4. If you can take x equal to 4, 4 plus 1, 5, like that. So same is applicable, whatever the value of x. So initial step, we have to skip all zeros till you will get a blank. Then blank is replaced with 0 and moves right, then halts. Then write in the final Turing mission. A final Turing mission m equal to q sigma tau delta q naught blank and final state. Now write down all the tuples where q equal to, here we used only two states, that is q naught q1. Then sigma equal to what the given input contains. It contains unary, that is 0. Then we used 1 also, encoded value separator. Then tau equal to, you can take all 0, 1. Then blank also we have to consider. Then q naught is the initial state. Q naught is initial state. Then q1 belongs to f is final or accepting state, and delta is b is anyway blank symbol. B belongs to tau is blank symbol, and delta is given below. Delta is given below. Here we have only two transitions. So the first one is delta of q naught on 0 equal to q naught 0, then moves right. The second one, delta of q naught on blank equal to q1 0, then r. So only two transitions. Now draw its transition diagram. Transition diagram. Here we have only two states. Let us take the states within circles. Now q1 is the initial state. Then q0 is the initial state. Then q1 is the final state, apparent within double circle. Now the first transition, q0 on 0 loop, 0 by 0 moves right. The second transition, q0 on blank, blank by 0, then moves right. Then similarly, draw its transition table. Transition table. So here we have only two states, that is q by tau. Here the tape symbols 0, 1, blank symbol. Then add on the transitions here. The states are q0 and q1. Now q0 on 0, what is the right side move? q0 0 or then q0 1, you don't have any transition. q1 on blank, the right side move is q1 blank by 0, then moves right. From q1 on 0 1 by, you don't have any transition. So this is the transition table. This is initial state q0, then this q1 is the final state. Then to accept the input, let us take x equal to 3 for example. You can 0 0 0. Now you can see, you can take the initial configuration q0 0 0 0. Then q0 on 0, just skipping, then it moves right without changing state. Then 0 again skipping. Then q0 on 0 again skipping. Now what you will get here? Blank. Now whenever blank is found 0 0 0, this blank is replaced with 0. Then it moves right by changing state q1 blank. Now here you can see Input we have taken 3 zeros. Then output what we got 4 zeros. Here now it is in the form of alpha 1 some p alpha 2. Then where p belongs to f, that is q1 belongs to f. Therefore, the string or input, the string 000 is accepted by Turing machine M. So this is very simple comparing to design of Turing machine for languages. For computable functions, it is very simple. Now let us come to another example. One more example we will see here. So this question frequently we will get in examination sometimes. Construct a Turing machine M to compute the concatenation or addition function. So it is defined as f of x comma y, which has two arguments denoted by x plus y, or f of x comma y equal to xy. See, the final result of these two functions is same. If you can take concatenation or addition, the final result is same here. Don't confuse. Solution. So given function f of x comma y equal to xy, so which is concatenation, then our addition is denoted by f of x comma y equal to x plus y. This is addition. So now input, let us assume input, let x equal to 3, y equal to 2. Then it is represented as 0 power x separated with digit 1, then 0 power y equal to 0 power 3, 1, 0 power 2 is stored on tape. That is the initial configuration. Now you can see, therefore, the Turing tape will be first 3 zeros separated with digit 1, then 2 zeros followed by blank symbols. So this is the initial configuration of tape. Initial configuration. Then let us calculate the output. Output f of x comma y equal to x plus y. So that is, what is f of x comma y? X equal to 3, y equal to 2. F of 3 comma 2 equal to 3 plus 2 equal to 5. So this can be represented as 0 power 5 equal to 5 zeros. This is the output string, which can be stored on the final configuration of the tape. Or if you can take concatenation, f of x comma y equal to xy. That is f of 3 comma 2 equal to 3, 2. So this can be represented as 0 power 3, 2. That means powers 3 zeros, 2 zeros. So here you can combine all the zeros. Finally, you will get 0 power 5 only. Here also 5 zeros. So therefore, final configuration is final configuration of the Turing tape. What it contains? 5 zeros. 1, 2, 3, 4, 5, followed by blank symbols. So this you need to get. So now here, what you have to do in the initial configuration, you can see in between we have 1. What you have to do? We need only all the zeros. 1 is not required in the final configuration. Then what you have to do? All zeros you can skip till a digit 1 is found. Whenever 1 is found, change the state. 1 is replaced with 0, then moves right. Then at the new state, further any zeros, all you can skip till you will get the first blank symbol. Why? Because whenever you can replace 1 as 0, here 3 plus 4 plus 2, 6 zeros you will get for this input. Then one extra 0 is there. So then what you have to do? That extra 0 needs to be replaced with blank symbol. For that, what you have to do? You can move right till you will get first blank symbol. Whenever first blank symbol is found, then you have to move left immediately before blank, whatever the 0 that is replaced with blank, then it moves right, then halts. Then our output is satisfied. Like that we have to do. So whenever extra 1 is there, so if any symbol not required, so that you can replace with blank. But which one you have to replace blank immediately after seeing the first blank before the blank symbol? That is replaced with blank or whichever the thing required. So now, as for this, write down the transitions one by one. So first step, first take the tape 0, 0, 0. Here we have taken 3 zeros. That is x equal to 3. Then y equal to 2. That is 2 zeros. Now blank. Now let us take the initial state. Then the read write head will be positioned on the leftmost argument first bit. That is 0. So this is first argument x. Now this is second argument y. In the first argument leftmost bit. So it is 0. Now here the transition is delta of q0 on 0 without changing state. You can skip all zeros till you will get a digit 1. So this is the first transition. So now let us skip all this. Then diagrammatically this will be first here 0, 0, 0, 1, 0, 0. Here only the state is moved towards right without changing state q0. So again the second 0 also you have to skip using the same transition 0, 0, 0, then 1, 0, 0, then blank. Now your finite control will be at third 0 with the same state. Then skip this 0 also. Now this will becomes, so whatever I am drawing here, this is configuration of the Turing machine, each and every step of the design. So now you are at the bit 1 with the q0 state. So whenever the digit 1 is found, what you have to do? That 1 is replaced with 0. Then you have to change the state. So whenever a digit 1 is found, replace 1 by 0 and moves right by changing the state. By changing the state. So then, therefore, the transition for this is delta of q0 on 1 equal to, it is changing to q1, then 1 is replaced with 0, then it moves right. Now this is the second transition. So then see the configuration of the tape after this move. This will becomes now 3 zeros remain same. Now 1 is replaced with 0, this one. Then moves right. Then right side what you have further 2 more zeros are there. Now the control will be at after replacement, whatever the next cell, what it contains 0. Now you are at q1. So now here, now skip all zeros at q1 till to get a first blank symbol. A first blank symbol. Now for this, write down the transition. Now the transition is you are at q1 0 without changing state, q1 0 by 0, then it moves right, skipping all zeros. Now the configuration will be, now draw the Turing tape configuration 0, 0, 0, 0. Now 3, 4 zeros. Then the fifth 0 is skipped. Further, what we have? So now after skipping this, now you are at the sixth 0 with q1 state. Again, you can skip this one also. Now 0, 0, 0. So total Now three six zeros. Now it moves right without changing state. Now you are at Q1. So now whenever first blank is found, then replace blank by blank and moves left by changing state, and then the immediate 0 is replaced by blank and moves right by reaching to accepting our final state, by reaching to accepting state. Therefore, now see the transition. You are at now Q1. Whenever blank is there, Q1 and blank equal to, it changes the state. Blank is replaced with blank, then it moves right. Now this is the fourth transition. Then see the configuration of the tape now. Here what you will get? 0, 0, 0. Then total 6 zeros. Then here blank. Now you are at the rightmost 0 cell with Q2 state. For this also we mentioned in the above what we have to do. Delta of Q2 on blank equal to, it goes to final state. Let us say Q3. So here now you have 0. Q2 on 0 equal to Q3. 0 is replaced with blank. It goes to Q3 state. Then it moves right. Now here Q3 belongs to F. Now see the configuration. The configuration will be now. So now it will get only 5 zeros. Why? Because the 6 0 is replaced with blank. Then it moves right. Again one more blank. Here Q3. So here Turing machine halts at Q3 by keeping x plus y or concatenation xy on the Turing tape. Now you can see therefore here 1, 2, 3, 4, 5 zeros. So output is 1, 2, 3, 4, 5 zeros. This is nothing but 0 power 5. Finally, here you can see it satisfies the output 0 power 5, 5 zeros. So that is the logic. Here simply whenever more than one integer is there, those are all represented separated with digit 1. First you can calculate what is the output value. Again that you can convert into unary form with 0 power I format. So to get that, whichever things not required, those are all replaced with blank, or with whichever the output is lagged. So you can use that output value. Like that you have to proceed. Therefore, final Turing machine. Now you can write down the Turing machine followed by its diagram and table. M equal to Q sigma tau delta Q naught blank B and final state. Where here what are the states we use? Capital Q equal to Q naught, Q1, Q2, Q3. Then sigma equal to what input contains? X comma Y. So here combination of 0, 1 only. Then tau equal to 0 1 comma blank. Then q naught anyway belongs to q is initial state. Then blank belongs to tau is blank symbol. Then f equal to q3 is final state or accepting state. Now delta is given below, and delta is shown below. Add on all the 5 transitions what we obtained in the above. The first one is delta of q naught on 0 equal to q naught 0 or the second one delta of q naught on 1 equal to q1. 1 is replaced with 0, then it moves right. Then at q1 skip all zeros. Delta of q1 on 0 equal to without changing state. q1 0 is replaced with 0, then it moves right. Then whenever the first blank is found at q1, q1 blank equal to it goes to state q2, blank is replaced with blank, then it moves left. Now whenever it moves left at q2, whatever the 0 before blank, that is replaced with that 0 is replaced with blank, then it moves right, then it goes to final state, that is q3. q2 on 0 equal to q3 blank, then it moves right. Now draw its transition diagram. Transition diagram. Here we have q0 to q3. 4 states are there. So let us take q0, q1, then q2, then q3. Here q3 is the final state represented within double circle. q0 is the initial state. Draw and prefixed arrow or labeled with the phrase start. Now include all the transitions. q0 on 0 equal to 0 by 0, then it moves right at the same state. So whenever it sees 1 replaced by 0, then it moves right, goes to q1 state. At q1 state, any zeros are there, skip zeros and moves right. So at q1, whenever it sees a blank symbol, blank is replaced with blank, it moves left, it goes to q2 state. At q2 state, whenever we have 0 replaced with blank, then it moves right, then it halts. So this is the transition diagram. Similarly, transition table. Transition table. Now q by tau. Here the table symbols are 0, 1 and blank. Now the states are q0, q1, q2, q3. First one is q0, second one is q1, third one is q2, then fourth one is q3. Now write the right hand side of the MOOCS on the respective tape symbols. q0 is initial state, q3 is final state. Now q0 on 0, what we are getting, the right side move is q0, 0 or. Then q0 on 1, what you are getting, q1, 0 or. Then q0 on blank, you don't have any transition. Then q1 on 0, we are getting q1, 0 or. Then q1 on 1, you don't have transition. q1 on blank, you are getting q2 blank left. Then q2 on 0, we have the transition. q2 on 0 is going to q3, 0 by blank, then moves right. Then q2 on 1, no transition. q2 on blank, also no transition. Then q3 on 0, 1 blank, no transition. Now similarly, verify the any one input to accept the input. So input you can take compulsory with combination of with digit combination. Suppose here 3 zeros, 1, 2 zeros. Now let us check with this. So then Q naught 0 0 0 1 0 0. Then skip all zeros till you will get 1. Now 0 Q naught 0 0 1 0 0. Then again next 0 also you can skip Q naught 0 1 0 0. Then next 0 also you can skip. Now Q naught 1 0 0. Now whenever 1 is found, so what you have to do? That 1 is replaced with 0. Then it moves right by changing the state Q1 0 0. Now at Q1 0 you can skip all zeros. Now it moves right by skipping 0 by 0 Q1 0. So again it moves right by skipping this one. I will get 0 0 0 0 0 0. Now Q1 blank. So whenever the first blank is found, so what it is doing? 3 3 6 zeros. So it moves left by changing the state, that is Q2 0. Then further blank remains same. Now at Q2 0, what it is doing? That 0 is replaced with blank. Then it moves right by changing state to Q3. So now this is replaced with blank. Then moves right to Q3. Again blank is there. Now you can see 3. So here this is replaced with blank. Now you will get only 3 2. Here why one extra 0 came? So here 3 3 6. So here actually one extra 0. Now you can see this extra 0 is replaced with blank. Then the Turing machine halts by keeping 3 plus 2, 5 zeros on the tape. Now this is in the form of alpha 1 P alpha 2. Here P equal to Q3, which is belongs to F. Therefore, the input is accepted. The input 3 zeros, 1, 2 zeros is accepted by Turing machine F. So this is the acceptance. So like that, any given function by representing in the form of unary string using 0 power I for every argument that can be stored on the Turing tape, then the final configuration you need to derive by designing the Turing machine or constructing the